Hi, I'm Olivia, everyone's favorite math teacher, and in this video, we're going to go ahead and put all of those skills we've been working on to the test and see what we can do in applying calculus to actual problems. We already know that calculus came from the idea of trying to figure out how quickly an object is moving at a given moment in time, and that algebra failed to be able to calculate this, right? So the entire idea is that an object is moving, and if its speed is changing, going around a curve, or just anything odd is happening, at a given moment, we know it has velocity, but we weren't able to calculate the velocity in an instant. Well, it turns out there's a lot of other situations where this might come up, and we might want to know when those changes are happening so that we could utilize those calculations. This example comes to us from biology, and this is a cell is absorbing water, and as it absorbs water, it's growing. And the cell will grow in two ways. It will both expand in a linear way as its radius grows, but as it expands, it's absorbing water, which is the volume is increasing. And what we're interested in is how do those two things interact? In other words, how much volume is required, or how is the volume changing as the radius grows? So what is the rate of change of the volume in relation to the rate of change of the radius, right? So what we're looking to calculate here is what is the volume change when the radius changes from 5 micrometers to 8 micrometers, or 5 micrometers to 6 micrometers, or 5 micrometers to 5.1 micrometers. Now, hopefully at this point you recognize this is an algebraic calculation. So we set up the function, which is just our volume of a sphere calculation. And then this is doing calculus, because we're asking not what would be the change in that volume across the duration, but what is the change at a given moment, and we cannot calculate that using algebra. That's where our calculus comes in. And then what we're asking down here in the bottom is, what do we notice about that instantaneous change? What is that relationship between the radius and the volume? Where does that relationship come up? And what we mean by this is the change in the distance at a given moment turned out to be the velocity. We gave that a name, and it was a very important thing. So is there a similar relationship in the change in the radius and the volume here? We'll look at this in 3, 2, 1. So to answer this question, what we need to remember is that when we're looking at these kinds of problems, we're identifying the independent and the dependent variable. What is changing? What is causing the change? And ultimately, a derivative is looking for a rate of change. And we also have to understand the difference between the average rate of change and the instantaneous rate of change. Because the entire idea here is just like the whole concept with Zeno and the arrow, is that things change in a continuous, smooth go. They don't change at a moment and then no change, and then a moment, and then no change, and then a moment. And so when we calculate things that way, we often come up with incorrect but maybe close results, okay? And that's what this problem is demonstrating. So the first part of it asks you to calculate the average rate of change, and that's the algebraic answer, where we look at an interval and we calculate based on the endpoints using our slope formula. And for that, we do exactly what we do. We take our formula, so our independent variable is the radius, because it's the thing that's causing the change, and then our dependent variable is the volume, it's the thing that's changing, and we simply go our volume with radius 8 minus our volume with radius 5 divided by the radius 8 minus radius 5, right? And that's going to get us not our volume, but the rate of change of our volume. If we wanted to figure out our volume, we would have to then multiply this times the radius, or the volume at that point, right? And that would tell us the rate of change, so that'd get us to the next point, okay? I'm sorry, times the radius at that point. Yeah, the 5, yeah, I was right, the radius, okay? And the point there is that if we were to do that, you'd notice that we would get a different answer for each of these at that starting 5, okay? But we would get a closer answer here for the actual volume at 5 than if we were to use this version, okay? And then this would get us our actual rate of change at 5 micrometers. And you'll notice that that's actually very close to the 5.1, okay? Because here we took our derivative. And what's interesting here is that we want to actually notice something. When we first looked at a derivative, we had a derivative was a velocity, because the derivative we looked at the first time was the rate of change of position. And the change in position is velocity. But here we're looking at a change of volume compared to radius. And that volume, that change in volume compared to radius, it turns out is surface area. And does that make sense? Would the change in volume compared to radius be surface area? Does that compute? Is that a unit that we would use for that? And if you think it through, it actually does make sense, because if you think about increasing the volume of something, and don't think about it like a cell where we're filling it full of something and it's expanding like a balloon. I would say the easiest way to think about this is, think about making a candy, like a gobstopper or something, right? Where you're making it in layers. How does that get produced? Well, you start with the inside, a small thing, and then you dip it and you put a layer on, and then you dip it and you put a layer on, and it produces in shells of a layer and then a layer and then more and more surface area. Or think of like a pearl in an oyster. So yeah, actually, the volume increasing as a rate of increasing surface area absolutely makes sense, and is completely the way it gets done in nature when you think about spherical objects being constructed in nature. Yeah, this is exactly how it gets done, and it completely jives with the way that the calculus predicts that it would be done. So we're going to look at a few more examples of how calculus gets used in other forms of science, and then after that, there's going to be a few practice problems for you to try. So in the example we just looked at, we saw how we can use a derivative to examine something that isn't just velocity, or looking at an arrow in flight. And here are 3 other examples from science where we're looking at a rate of change that matters and that we use to compute something that is rather important to us. For example, isothermal compressibility talks about the compressibility of a gas at a fixed temperature, something that's rather important for hydraulics. When we're looking at laminar flow, the velocity gradient tells us how fast we can push a fluid through a pipe to maintain laminar flow, something that we care about if we're doing things like putting medicine through small capillary tubes. And then marginal cost tells us about the cost of producing items per unit at large scale. So when we're talking about, for example, economy of scale for things like global economies. So we're going to be looking at a couple more problems that have rates of change that aren't just something based on time. Here are a few problems for you to work on. And remember, when you're looking at these, try to identify the independent variable, the dependent variable, and the function you're going to have to use to find your rate of change. Try to do at least one of the calculations by hand, but if you do find them to be a little bit tedious as you're working through them, don't hesitate to use your technology to your advantage. So I hope this brief review and exploration of calculus and other sciences was helpful. And as usual, the answers to the practice problems will be at the end of the outro. And if you have any questions, feel free to drop into the comments or join us on Discord. In the next video, we're going to be looking at something that students often find difficult: related rate problems.